Hey guys, I hope everybody had a wonderful weekend. This lecture's for Monday. So we talked last time about finding global maxes and global mins. So you're going to want to go back, look at that lecture if you haven't. You're going to want to make sure you have all of those definitions and some of the theorems that we talked about last time. Extreme value theorem down in your notes. We'll probably have a quiz next week. I'll be more specific about the date and the sections, but it'll be definitely related to chapter 4. As far as like your reading, I know you've read this already, but we're going to be talking about concavity, so I think it's good to read section 4.2 again. And these are the homeworks that I want you working on in 4.2. 1, 3, 5, 7, 11, 29, 31, 33, 37, 39, 41, 51, and 57. Now the first few ones are graphical, trying to decide whether or not some region is concave up or concave down when the function is concave up and concave down. So the first thing I want you doing is I want you just copying all this down. Okay, you have these definitions here. Sorry they're a little light, my marker was running out. But what I want you to do for the first probably 8, 9, 10 minutes of class, 5 minutes of class, is just copy all of this down, okay? And I'll just sit here like this, and you can pause me. Sorry so much about the screw up on the last video. I put music in it, wasn't even thinking, I just put up a popular song, didn't know what it was, and then got flagged for a copyright violation. I was just like, you've got to be kidding me. But somehow YouTube muted it out, so those mute parts was some song about some monkey, I forget. I apologize. Okay, so write all this down, and then I will start. Okay, all right, now that you've written it all down, let's talk about these a little bit, okay? Okay, my definition, F is concave up. So this is definitely going to be on our third test when we're thinking about this. F is concave up on an open interval AB. Now intervals of increase and decrease are almost always closed intervals, unless we have a problem with the domain, okay? Again, I'm not going to worry too much about it, okay? Critical points are domain values. They're just values on the x-axis, okay? They're places where the derivative is 0 or the derivative doesn't exist, but they got to be in the domain. Okay, local maxes and local mins and global maxes and global mins, which is what we were talking about last time, they occur on the y-axis. They're range values. They're f of c values. Okay, critical points domain, maxes, mins, range, intervals of increase, decrease, closed most of the time. Concavity talks about the graph, and typically we talk about being concave up on open intervals. They're exclusively open intervals. Okay, so we say that f is concave up, a function f is concave up on the open interval AB if f prime as a function is increasing. Now notice, this is not saying the derivative is positive so the function's increasing. This is saying the derivative as a function itself is increasing. Okay, this function f prime is increasing on the open interval AB. Okay, so that's the definition of what it means to be concave up. Now the definition of concave down is almost identical. I mean, you're like talking when the words are identical, except we got up down. AB if f prime is, instead of increasing, we have decreasing. Okay, so the definition that a function is concave down is that the derivative as a function itself, not f, is decreasing on the open interval AB. Okay, the last major definition from section 4.2 is this idea of a inflection point. Okay, the point C, f of C, is an inflection point of f if f changes from concave up to concave down. Okay, if concavity changes across this point on the graph, we'll talk about what it means to be concave up and concave down throughout the lecture. Okay, but if it goes from concave up to concave down, that's one possibility. or it goes from concave down to concave up. That's another possibility. Then this point, CF of C, we call it an inflection point. So a place on the graph where concavity changes is an inflection point. Now it's got an x coordinate and a y coordinate because it's an actual point on the graph. Critical points, domain values, just x values. Local maxes, local mins, global maxes, y values. Okay? This is a domain range value. It's an actual point on the graph of the function. Okay. We do not use the definition. We do not use the definition much because we've got this major theorem, these two major theorems, which help us here. Now, there may be some cases where the derivative does not have a second derivative, where you can't take the derivative. So these definitions are still important. However, in this class and in most calculus classes, okay, these are the go-to. But I think about how I could trick you on a true-false. I could say, this is the definition. And if you bite, you're wrong, because this is the definition. The definition is that f prime is increasing on the open interval. However, one of our theorems that we showed was that if a function, if we want to show a function's increasing, we could use the definition. Remember what the definition was. We have, if you have that x1's less than x2, it implies that f of x1's less than f of x2. That's the definition. That's the working definition of what it means to be increasing. However, this is a nightmare. This is a nightmare to use. Okay? However, we argued, and the way that we've been showing increasing and decreasing throughout section 4.1, and then we were even talking about it some last time in 4.4, was that if the derivative is positive on an interval, then that means the function's going up. Remember, we created our sign charts for our first derivative. Wherever it was positive, we drew an up arrow. Wherever it was negative, we drew a down arrow. And then we read off that our local maxes, local mins. Okay, when we're looking for global maxes, global mins, it's not that much harder. We look at our local maxes, local mins, and we look at our two endpoints. Okay, the function evaluated at the two endpoints. However, using this is not what we want to do. We don't use the definition. The same thing here, we don't really use the definition much. If we want to show f prime as a function, like for example, if I wanted to show the function g was increasing on some interval, if I want to show g was increasing, then what I want to do is I want to show that g prime of x is greater than 0, don't want that symbol, for all x in AB. I would want to show the derivative is positive on that interval. However, now my function is not f. My function is f prime. So I can still use the same idea. I can still use that same theorem that if I just let g be f prime, I want to show f prime is increasing on the open interval AB. Well, then I would want to show f prime's derivative. I'd want to show the derivative of f prime is greater than 0 on the open interval AB. Or that would imply that f double prime, because the derivative of the derivative is our second derivative, is greater than 0 on the open interval AB. Okay? So our theorem back in section 4.1 comes to save us again here in section 4.2. Okay? So in order to show that a function's concave up, the technical way we go about it is we show that the second derivative is positive on some interval. To show it's concave down, we show the second derivative is negative on an interval. If the second derivative is positive on an interval, then the first derivative is increasing. In the same way, if g prime is positive on the interval, g is increasing. So in this case, this g is f, and my g prime is f double prime, is the derivative of f. Okay? And so that's roughly the theory. That's roughly the theory in this section. The problem with this section is the second derivative often gets messy. If it's not a simple polynomial, the more derivatives you take, the nastier it gets. I mean, think about square roots of stuff and quotients of things. You use quotient rule, and then you want to take a derivative of that. So these problems can be really messy because you're looking at the second derivative and trying to create a sign chart for the second derivative versus just the first derivative itself. Okay, so that's a little bit of a warning. The problems here, some of them is going to be a little bit more complicated just because you're dealing with the second derivative. But it's much like what we were doing with increasing and decreasing. Okay, almost the technique will feel very, very similar, but you've got to remember it's the second derivative when we talk about concavity. Dr. Warren, get out of the camera. It's the second derivative. Okay, so what I want to do now is I want to show you that knowing information about the function and even knowing information about the first derivative ain't enough to really make an informed decision. Do this out there. Let me put this back here. I'm going to give you two scenarios. Okay, so what we have is we're going to have two graphs of two functions. Okay, and well, let's just be 0 months, 21 months. What am I? There you see the dyslexia in full exposure. Okay, 12 months. So this is being measured in months. Okay, and this is 0 months, and this is 12 months. Okay, so we're looking in our domain over a 1 year period. Okay, so now let's hope this is not true. Let's suppose that f of 1 or f of 0 is, let's just say, 100. And over here, we got a function g of 0 is 100. So we know at 0, we're up 100. And we know at 0, g's up 100. We know f of 12, at 12 months, it's 2,000. And g of 0 is 2,000. Now my scale's kind of messed here, but let's just call this 2,000. And this 2,000. And so we also know right here, this is a point on the function. And that's a point on the function. Now let's imagine that both of these scenarios are modeling the coronavirus. Okay, let's imagine that both of them. I know this is maybe okay. Maybe we don't want to do this, but let's just say it's modeling the coronavirus. Okay, and so maybe this is representing in thousands of cases. So at 0 months, we've got 100,000. We've got 100,000 cases in both of these models. And at this, we've got 2 million. We've got 2 million cases. Okay, that's probably really underestimation. Okay, but let's just say we've got 2 million at both of these, and let's suppose that we also have this other piece of information that the first derivative of x is greater than 0 for all x in the interval 0 to 12, and that g prime of x is greater than 0. For all x in 0 to 12. I realize I just can't bend my knees much. That's something like I look at myself in my videos. I'm like, oh my gosh, these poor kids. They got to see this. Okay, so we've got the derivatives positive here, and we have the derivatives positive there. Now, if the derivative is positive on the interval, what does that tell me about the function? And you're like, well, Dr. Warren, I've been paying so good attention in class. If the first derivative is positive, it means the function's going up. Okay, well here the first derivative of g is positive, means the function's going up. You're like, Dr. Warren, these are the same functions. They start at the same place, they end at the same place, and their derivatives are always positive, so they're always increasing. Now I'm going to ask, like, which model do we hope the coronavirus is following when we're looking at this. And I'm going to show you, I'm just going to draw both of these functions. This one looks like this. This one looks like that. Now I've got to ask, do they both start at 100 at 0 months? And do they both end at 2000 at 12 months? Is this one always increasing? And is this one always increasing? So both of these graphs meet these scenarios. But which one would you want to be the model? Would you want the first one or the second one? And would it matter? And would it matter? If this was stocks, it would be a very different kind of thing. If this was your stocks, you'd be kind of like, well, let's hug number one, okay? Because I started off slow, but it looks like I'm building momentum, okay? I'm building momentum, okay? Here, we started off quick if this was a stock, but we're losing momentum, okay? And you're like, this is getting a little disappointing. Maybe it's time to sell. Maybe it's time to sell. This is the coronavirus. This is really disappointing, okay? Because it means we're increasing at a faster and faster rate, okay? Okay, we're accelerating as we move along here. However, this one, we're moving at a slower and slower rate, or we're deaccelerating as we move up. We're deaccelerating as we move up. So the whole point of this is just to show you that knowing information about the function itself and knowing some information about the first derivative is often not enough to make the right choice, okay, if you're given a mathematical model. You want to know something about the shape of the curve, okay? And that's where this idea of concavity comes in. Okay, remember the definition was if the first derivative is increasing. Now, we got a graph. The first derivative means so much more than slopes of tangent lines, okay? I often ask students, well, what's the first derivative? Oh, a slope of a tangent line. But remember, the first derivative means so much more than a slope of a tangent line. But graphically, if I look at the slopes of the tangent lines here at various points, they're always positive. Those slopes are always positive as I read left to right. And here, the slopes of the tangent lines are always positive. They're always tilted at an upward angle as we move from left to right. Okay, but what do I notice about these slopes versus these slopes? And so hopefully what you're seeing, at least a little bit intuitively, is that these slopes get steeper and steeper, or that the first derivative values are getting larger and larger, or that the first derivative is increasing as we move along this kind of a function. Okay, we're here just the opposite. Yeah, they're going up, but here they're steepest at the beginning, and then they get less steep, these little tangent lines, these little tangent slopes, as we move along. Or in this case, as a derivative, the values, even though they're positive, they're getting less and less positive. Where here it almost looks like it's almost reached zero. Where here it's almost reached zero. Where on this side, no, this doesn't look like this is zero. That looks steeper still as we're heading off there. Okay, so here it looks like the derivative values are decreasing, where here the derivative values are increasing. Okay, and that's where the definition comes in. So if the derivative itself is increasing, it creates a shape that looks like this. If the derivative itself is decreasing, okay, but the function is increasing, okay, then it gives us a shape like this. And this reminds me of a story. So let me just tell you this. In 1977 was by far, it was by far the worst snowstorm I was ever in. Okay, this was like when I remember Dick Goddard on the TV news, this was before they had computer graphics, had his like low pressure with so many rings around it, it looked like Katrina, okay? And that's the best way I could describe this snowstorm. It was like a snow Katrina, okay? In Ohio, we were kind of used to snow. We had drift fences. We had things to deal with it. Roads got cleared. I mean, I remember driving on top of snow to get to school, okay? But we were out of school for 4 weeks. We were out of school through January into February. We didn't have power for a couple of days, and we were in a city, okay? I don't ever remember snow being like this ever. And I just like, okay, for the first couple days, it's kind of like being quarantined, okay? Except like you can go outside now. There was no, I mean, we could go outside, okay? But I mean, like, we had so much snow. In fact, it's hard for we, on one side of our house, the wind was blowing so hard, okay? This was a ranch house. It was bare ground. It was bare ground. There was like no snow there. You could see grass poking through. On the other side of the house, you could literally walk up the snow mound, okay? And then you would climb around, and then you would drop down onto the roof. The snow itself was probably 14 feet high, and we would climb down onto the roof. The entire side of the house. And I know you don't probably believe me, but if you Google images, okay, I'll just bring you over here. Let me just, sorry. I'm not sure you'll be able to see this. But here's an image right there, and you can see that is a school bus. You can see that's a school bus, and these people are climbing up there, okay? Our snow was higher than that at our house. You know, like, Dr. Warren, what does this have to do with concavity? Well, humor me a little bit, okay? So the first couple days of the snow siege, okay, our snow quarantine was, let me just make sure I've got this board kind of in the picture. I think maybe a little bit there more. Okay. The first couple days was fine. We went outside, no school. I was a failing student anyhow, so it didn't matter. I was like, okay, exciting. I don't have to turn in my homework. Let's go out and make snowmen. Let's do other things. And then we were just like, after about that, we were like, okay, I'm bored. Let's make snow forts. I'm bored. So like by day 4, being stuck with your brothers and sisters and your family. My dad was a doctor. He took 2 days off work. He climbed through snow like that to walk 2 miles to get into work. Okay, that's how dedicated he was. He probably just wanted to get away from us 6 kids. I mean, that was probably one of the major things that was driving us. Okay, but then we were like, okay, we were bored, and so we made the snow angels. And then my brother Doug got this amazing idea. He went out and got one of the big Rubbermaid trash cans, and we found that if we packed the snow full of in that Rubbermaid trash can, you could turn it over and pull it off, and it would work the same as making like sand castles, just massive sand castles. Okay, and so Doug got the idea to actually. Here's maybe our house here. Okay, the snow is like this, nothing here, snow coming down there. This part of the house is covered. This snow's here. Of coming up here, here's our kind of front door, our double front door. Of coming onto the roof and building these snow sandcastles on top of the roof. Okay, and then what he would do is he would stand out by a pine tree. Okay, so here's our pine tree over here, and he would hide, and he'd wait for one of my little brothers and sisters to come walking out, and I would be up here, standing there, and then he would give me the go sign from down here, and then we'd push that volume of snow onto this poor child, who would then be down on the ground, and then we'd push another one on top of him. And I'll tell you what, that never got boring, okay? I mean, we were 4 weeks straight of doing that, and it never got boring. You think these kids would learn too, but you know, I guess you get knocked down a few times of them. So one morning we're out there, okay, it's probably 10 o'clock, we're setting up the trap, and my brother gives me the go sign. He gives me the go sign. So I push down the first snow trash can full onto. But this time I don't hear the familiar thud going down on the ground. You know, I'm like, okay, well, maybe they're getting ready. Push another one down, again, I don't hear the familiar thought, okay? But what I do hear is this something that sounded really like the abominable snowman. It was like, okay? And then I knew that sound because I knew it was Dad, okay? And you gotta remember, my dad was bench pressing 450, okay? Not then, but back in his heyday, one of the world-class discus throwers of his time. Okay, the best ones were in the U.S. at that point in time, and he was in that group. Never made it to the Olympics, but was in meets heading into the Olympics. And then I heard, "Get down here now," and so I was like, "He's gone. He's always gone by like 7 a.m. He's always gone. It's 10. Something must have happened. He had a late night." And so I climbed down off of here, walked over, met him there, and he was like, "I'll deal with you when I get home." And I was just like, "Oh, you've got to be kidding me." So the rest of the day, all I did was just wait for him to get home and just get ready for my punishment, okay? And then he came home, and I just kind of like looked sheepishly, didn't pay it, and I just waited and waited and waited for my punishment, thought about putting on multiple layers of underwear just in case. But then he must have forgot. I don't know. I mean, I was trekking through the snow. Who knows what was happening at the hospital? But he forgot. And you're like, "Well, Dr. Warren, what does this have to do with concavity? What does this have to do with concavity?" Well, when I was pushing snow onto my brothers and sisters, I was smiling. I was so happy. I was smiling. Okay? And even when I was pushing snow and I realized I thought it was my brothers and sisters, but it was my dad, I was smiling. But the moment I heard, okay, that frustration coming out, that smile turned into a frown, okay? And then I was frowning all day long. I was frowning all day long until I realized maybe he forgot. And then that frown turned back into a smile. Okay, so this is the moral of the story. This is the moral of the story. Okay, when you're concave up, you're smiling. When you're concave down, you're frowning. Okay? Places where you go from smiling to frowning, we call those inflection points. Those are my inflection points. So you can see here, throughout my day, there were 2 inflection points. When I was pushing the snow down to where I realized, oh my gosh, it was Dad, okay? To where Dad came back, and then he forgot, and that frown turned into a smile. Okay, so that's what I want you graphically thinking, okay? When you're concave down, the graph is frowning. When you're concave up, the graph is smiling. Dr. Warren, don't do that smile ever again, okay? When you're concave up, concave down. Okay, so we used to play this game with the girls. Okay, we would make things like this: happy face, sad face, angry face. Yeah, that was horrible. I mean, concave up, concave down, concave up, concave down. Inflection point. I don't think I can do that. Okay, so all right. So this is what I want you guys thinking. Now I want you noticing that on a smile, if you look at a smile, there's parts where you're decreasing. There's a part of a smile where you could be decreasing. There's part of a smile where you could be increasing. So in this range here, your f double prime would be greater than 0 because you're in a place where you're concave up, you're smiling, but your f prime would be less than 0. You're decreasing. On this side, your f double prime would be greater than 0 because you're smiling, okay? Concave up. And your first derivative would be positive. What kind of hieroglyphics is that, Dr. Warren? Because you're increasing as you move left to right. Similarly, on a frown, there's places where you're increasing and there's places where you're decreasing. Okay, so now what I want you to do at your seats is I want you to try to create the signs that you would have for the frown. Okay, so you guys go ahead. Let's see what you've learned by looking at that. What do you think that would tell me about the signs of the derivatives on this nice smooth function here on that frown? So you go ahead, you do that. You go ahead and mark those. You can pause me if you want to do it. Okay, but if I'm looking at it, okay, I know I'm increasing, so my first derivative is going to be positive. I'm frowning, so my second derivative is going to be negative. Going down, first derivative is less than 0. Frowning, second derivative is less than 0. Okay, so again, we can think of these as here I'm accelerating, but I'm decreasing. I'm accelerating, but I'm decreasing. Okay, and remember when we're talking about distance versus time, acceleration is always related and is always related to what's positive. What's positive? Okay, so I'm decreasing. I'm decreasing, which means I'm moving in a direction that I don't want to go, and my first derivative is positive. So I'm going the wrong way. But the acceleration's positive. It's helping me. I want to go this way. I'm moving this direction, but my acceleration's positive, which means then I'm slowing down. I'm slowing down to hopefully turn around. It's helping me. The acceleration's helping me. Okay, here I'm moving in the right direction and my acceleration's positive. I'm moving in the right direction so here I'm speeding up. Okay? And so you got to remember that with physics in general, that things aren't always what you think they should be. Okay? At least that's the way it was often for me. Okay, so now let's look at some examples. Let's look at some after I told you a story. So yeah, if you really get bored, look up The Lizard of 1977 and enjoy some of the pictures. Okay, so let's look at some functions, kind of like what I assigned in your homework, and then let's try to find out some of what they were asking. So here's maybe one. I think this was, I forget which exercise this was. Okay, and they're not asking for critical points. They're not asking for intervals of increase and decrease. They're not asking for local maxes and local mins. What they're asking for is when is it concave up? When is it concave up? And they're also asking what are the inflection points? Are there any inflection points? Okay, so the first thing I want to look when I'm looking at something like this, I'm going to ask what's the domain? Okay, you always want to think about it. And you see no square roots, no division, no problem. Okay, so my domain is all real numbers, continuities on the field. Okay, this we can take derivatives of it. So we take our first derivative. Hopefully everybody can do that now. Okay, minus 2x plus 3. Okay, so we've got that. And now, but we're asking about concavity. Are we working with our first derivative or are we working with our second derivative? But we're talking about concavity and inflection points. Right? And hopefully you said the second derivative. So hopefully everybody could take the second derivative. Derivative of 3 is 0. Derivative of this is negative 2. Okay, so now let's make a sign chart for this second derivative. Just like what we were doing in the other sections with our first derivative. Can negative 2 ever be 0? And the answer is, of course, no. It's not, it's always defined. Okay, so the second derivative for all values of x is always going to be negative. Is always going to be negative. Okay? And if the second derivative is negative, we've got a sad function. We've got a sad function. Okay? We are always concave down. So for this function, my intervals are concave down. are from minus infinity to infinity. Concave up, none. Okay, there's no intervals of concave up. And because you're always frowning and you're never changing you're never having that inflection moment, okay, when you realize you dumped snow on your dad, okay, where you're always concave down, there aren't any inflection points. There aren't any inflection points. And this kind of makes sense. This is a parabola. This is a parabola. Remember, when your A is negative, your parabola is flipped over, okay? And so graphically, you should be able to see that, oh yeah, I can understand why that would be always concave down. So there's a first really easy example. So now let's look at another one that might require a little bit more work, okay? Now again, as far as like being a author of one of these books, these problems aren't easy to write because you're having to write things for students where you're hoping the algebra isn't too overwhelming. So here's my second example. So here's my second example. So once again, we're asking, when is the function concave up? When is the function concave up? All right. Are there any inflection points? And I might throw a couple more things in, but we'll see. Now again, I'm asking for concavity. They're asking, when is it concave up or concave down? Is that the first derivative or is it the second derivative? Are we trying to analyze the first derivative or the second derivative with this? We're trying to find out when f prime is increasing and f prime or f prime is decreasing. But to do that, we're using our theorem that if we say look at the second derivative, we can figure out when the first derivative is increasing and decreasing. So hopefully you said, Dr. Warren, we're going to look at the second derivative. But to get there, we've got to take the first derivative. So go ahead and do that. You go ahead and take a shot at that. Okay, you can pause it and do it, but I'm now going to do it here. Hopefully you're getting 12x cubed minus 18x squared plus 1. Now what we're really happy is that they're not asking us for intervals of increase and decrease because this thing ain't going to factor, okay, and that would be a nightmare, okay, looking at that. We would probably want some kind of computer help, okay, if we were trying to find it. But they didn't ask us that. They didn't ask for intervals of increase and decrease or local maxes, local mins, or global maxes, global mins. They asked for when is it concave up and concave down. So I take the second derivative. Okay, and then I get that. Oh, Dr. Warren, seriously, okay. I get 36x. So 3 times 12, 2 times 18. Okay, this is the derivative I want to look at. So just like what we were doing before, let's create a sign chart for this derivative. So I want to find out when it's 0, because that's super helpful. Well, this would imply that 36x squared minus 36x is equal to 0. Now we can really appreciate the author because he made this a little bit. Is there anything I can factor out of both of those? Is there anything I can factor out? And you're like, well, Dr. Warren, I see a 36, but this guy's got an x and this guy's got 2 of them. So I can also pull out that. Now what would I have left here? Now remember, I want this times this to be that. Hopefully you can say that would be an x to give me that. And here, I would just need a 1. Okay. Using properties of the algebra of the real numbers, the only values that are going to make this second derivative 0 are when x is 0. That would make that guy 0. Okay? 36 ain't 0. And when x is 1. Those are the only values that are going to make the second derivative 0. So let's put those. I guess I should ask about the domain. Again, no division, no square roots, no problem in this class. So we would have our 0 and our 1. Now these are making the second derivative 0. I like to put those there because they help me. Okay, now all I've got to do is test. Since these are the only zeros, I just need one number here. Because this is continuous, if it ever changed sign, we'd have another 0. But our algebra says these are the only zeros. So let's take a number like, let's just say 2. Let's pick 2. 2's out there. So let's pick 2. We could pick 7. We could pick whatever we want. Okay, let's just pick 2. 36 times 2, positive or negative? Please say positive. 2 minus 1, positive or negative? Positive. Positive times positive is a positive. Okay, a number between 0 and 1/2, and you're like, It's okay. We just care about positive or negative. Let's pick 1/2. We got 1/2. 1/2 times 36, positive. 1/2 minus 1, negative. Positive times a negative, negative. Everybody's got to be negative in there, or we're going to have another 0, but these are the only zeros. Now we'll check a number out here, maybe like negative 12. Seriously, Dr. Warren? I don't care. 36 times negative 12, negative. Negative 12, take away another one, negative. Negative times a negative is a positive. Okay. So, since this is the second derivative, I'm not drawing arrows. I'm not drawing arrows. This ain't the first derivative, it's the second derivative. I'm smiling, concave up in this region, frowning, concave down in that region, smiling, concave up in that region. So if they ask for intervals of concave up, it would be between minus infinity to 0 and from 1 to infinity. And then let's weld that together with our union sign. Concave down. Zero to 1. Okay, now are there places where frowns turn to smiles and smiles turn to frowns? And it'll be like, well, Dr. Warren, you were smiling, then you dumped snow, then you were frowning, then you didn't get whooped, then you were smiling. So now we do have inflection points. Now remember, an inflection point is a point on the graph. It's got an x value, I don't know why I'm holding my fingers, it's got an x value and a y value. So this is the way I want you marking your inflection points. Because we're not testing, looking for global maxes, global mins, you can just leave them like this. My inflection points. When x is 0 and f of 0, there's my point on the graph. Okay, at that point, we change on the graph from smiling to frowning. Now I could plug this back into the original function. I put a 0 into the original function. This is an f double prime, it's not f prime, it's f. Don't make me come to that lens again. Okay, but I put it in here, 0 is easy enough to get. So the actual point would be 0, negative 8. But on a test or a quiz, I don't need to see that, since I've taken away your calculators, I don't need to see that, you trying to do that math. Well, the 0 you can do. And my other place where I change is 1. So another, this is not an interval. This is not an interval, guys. I mean, whoever came up with the interval notation maybe should have been punished, or the point notation, because it's real easy for you. Is this the 0 to negative 8? Well, that doesn't even make sense, right? I mean, this is clearly a point. But it can get confusing. 1f of 1. 1f of 1 is my other inflection point. And again, 1's not so bad. You could plug it up there. 3 minus 6, negative 3, negative 2, negative 10, if I did it right. So there would be my other inflection point. There would be my other inflection point. Okay, so when they're talking about with the coronavirus, when they're talking about looking for the inflection point, I mean, right now, sadly, we're moving like this as far as number of infections. What they're hoping for, okay, we can see, well, we're not smiling, but we are. We're concave up. They're hoping to look at a place where the number of cases increasing begins to slow down, and so that we would get a shape that looks more like this. So when they're looking for that inflection point related to these models, That's what they're talking about. That's what they're looking for at that point there. Right now, we're increasing each day, it seems. We're gaining more and more cases each day at a faster and faster rate. The number of cases are growing each day. The number of new cases are growing. We're looking at a place where that continuous, steadily begins to slow down. Okay, so it's important, all of this. It's important. Okay, one more example, then I'm going to let you go. Because they're not all polynomials. And I'm going to show you how you can deal with some things that are fractions. So let's look at one example, then I'm done. Okay. So let me see here. Let's look at this exercise. All of these are right from the book. Right around where the problems I assigned. Let's look at this. Okay. Now I'm looking at this and I'm trying to decide when it's concave up and concave down. Now I'm a little disappointed because it's a fraction. I've got to worry about my domain. I know that dude's not allowed to play. I know that guy's not allowed to play. He's going to cause division by 0, which is going to make all real numbers 0 if that was allowed. Okay, so let's try to find out when this is concave up or down. I got to analyze the second derivative. But now it's not so simple to take the derivative. Let's use quotient rule. The derivative of the top, 1, times the bottom, x plus 1. Remember, it's a minus in that sign, that rule. Minus the top times the derivative of the bottom. The derivative of x plus 1 is just 1 all over the bottom squared. Like, Dr. Warren, this isn't so bad. This isn't so bad. I can do this. Then we get x plus 1 minus x over x plus 1 squared, which is 1 over x plus 1 squared. Now, guys, a warning. I let you guys get away with for a long time not simplifying your derivatives, but if you're looking for concavity, you best simplify. Because you're like, well, that's not bad, Dr. Warren. Well, that's just the first derivative. Now we need to take the second derivative, which means we've got to take the derivative of this. Okay, we could bring this up, deal with the negative exponents. Sometimes kids mess that up. And in the end, we're going to be talking about signs. So oftentimes, it might just be best to just use quotient rule. The derivative of the top is 0, which is nice, times the bottom. Now remember, the bottom here is x plus 1 squared. Minus the top, 1, times the derivative of the bottom. We'll deal with that in a moment. Now, all over the bottom squared. You're like, ugh. Oh, this term's not bad. That goes away. We gotta use our power chain rule here. It's 2 times x plus 1 times the derivative of x plus 1. But that's just 1, so that's not bad. So it'd be 0 minus 2 times x plus 1 raised to the 1 times the derivative of the inside, which is just 1. And then maybe I'll simplify this down to x plus 1, 2 times 2, 4. Okay, let's keep simplifying so we can actually look at this. Minus 2 times x plus 1 over x plus 1 to the 4th. Let's simplify some more. If you got an apple over apple to the 4th, that's an apple to the 3rd. Down here. So this is what I mean. This is a little bit more involved. Okay, Dr. Warren, it's a lot more involved. Okay, it's a lot more involved than taking the derivatives of some of those simpler polynomials. Okay, now let's look at this. I want to create a sign chart for my second derivative. So the first thing I want to ask is, when is it 0? When is it 0? And you're like, well, you told me, Dr. Warren, that if you got a fraction and it's 0, The only way that can take place is if the numerator is 0. And my numerator is -2, which is never 0. So there's no zeros. There's no zeros. You're like, well, Dr. Warren, then are we done? No, we're not done, because is a bad place. There is a place where the domain goes bad, and it's still bad down here in my second derivative. It's also bad in my first derivative. So I need to mark that on there. On the test, it's not a critical point. You're like, Dr. Warren, it's making the first derivative not exist. But remember, one of the requirements is you've got to be a JMU student. You've got to be in the domain. This guy's not in the domain. He's an important point, but he's not a critical point. Dr. Warren, he seems critical. Stop. Okay, it's not a critical point by definition. Okay, so now all I've got to do is test. All I've got to do is test, okay? The numerator is always negative. So let's pick a number over here. There aren't any zeros, so everybody's got to be the same sign here, and everybody's got to be the same sign over there. So let's pick like 2. If I put a 2 in here, take a 2, and I plug it in for x, I get 2 plus 1 cubed, which is positive. So I've got a negative divided by a positive, which is negative. Over here, let's pick a number like -12. -12 plus 1 is -11. A -11 cubed, -11 times -11 times -11, that's going to be negative. And so I'm going to have a negative over a negative, which is going to be a positive. Okay, now again, this is the second derivative. This means I'm smiling, frowning. Okay, so if I'm looking here, and they're asking for intervals of concave up, it's from -infinity to 1, down, 1 to infinity. You're like, Dr. Warren, inflection points. Look, it's changing. It's changing here, Dr. Warren. It's changing. It was smiling on this side. It's frowning on that side. But guys, 1's not in the domain. Remember, it's a point. C, f of c on the graph. This isn't going to be anything on the graph. It's not even allowed into the function. So even though concavity's changing, there's no point there for it to be an inflection point. So my inflection points are none. My inflection points are none with this. Okay, so this is some 3 examples on looking at concavity. Okay, hopefully this makes sense. Again, hopefully you understand that the function itself in the first derivative is not enough. Okay, the second derivative tells us about the shape, and that makes a big deal as far as trying to make good decisions. Okay, thank you, and again, we'll probably have a quiz next week. Keep up with your homework. Keep up with your homework. I'm going to try to have Zoom office hours today. I'm going to try to have Zoom office hours. I'll send you an email about it on Monday morning. But I'm going to try to have Zoom office hours for those that want to see me, okay? I guess in this room, okay? But where we can communicate. I mean, I can't have everybody, okay? All 70 on there at once. But I doubt that'll happen. So we can have Zoom office hours. I'll figure out a time. Zoom only gives me 40 minutes. Zoom only gives me 40 minutes. It only lets me set 30 minutes, okay, on the free package. All right, thank you guys.